Hello, my name is Frits de Mul, and I would like to talk about the safe clinical application of the radiation of lasers. The contents of this talk will be: first, a physical mathematical explanation of how the calculation is performed. Second, a computer program and example of calculation. There are two options for the program available. First, as a subprogram of the Higirath nuclear package, that's a standalone package for your own computer, and second, a web application. More information can be found at this website. Scroll down to available software and presentations. Laser safety uses the nominal ocular hazard distance, and that is the safe distance to avoid eye or skin damage. The standard distance for eye safety is taken as 0.25 meters for a 10-second exposure time. And if the laser intensity there is too high, then you need to wear goggles, protection goggles. What is the damage to eye and skin? For ultraviolet, the damage is mostly photochemical and thermal. There is erythema formation in the skin and also thermal damage at the skin. In the blue-green region, there is also a possibility for damaging the retina, because the retina is sensitive for the colors, but erythema formation is not present anymore. In the yellow-red region, no photochemical damage anymore, but the retina and damage can occur, and also thermal damage. And for the infrared, thermal damage on both eye and skin can be present. What is the safety condition at the target? The intensity must be lower than the maximum permissible exposure, MPE. And both are expressed in watts per square meter intensities. And that maximum permissible exposure is tabulated by the EU and other international institutions. And that nominal ocular hazard distance, NOHD, is the minimum distance where that condition is fulfilled. What is the maximum permissible exposure? It is a function of the wavelength, of course, and the pulse duration, or when you have continuous laser, the length of the exposure. The pulse frequency is present. The angular substance, what is the viewing angle of the light source, how bright is the source, and the MPA formula were tabulated in this directive of the European Commission, and internationally IEC, and also the Netherlands directives. This is a plot of the maximum permissible exposure as a function of the pulse length in seconds, and here is the maximum permissible exposure in watt per square meters, and these are on both logarithmic scales. The different colors represent different wavelength regions, and each wavelength region has 3 values of alpha, and alpha is the angle of subtens, the angle you will see the waist of the laser seen as the source, and you will see it from the target. And here we took alpha is 1, 10 or 100 milliradian, and that corresponds to 0.06, 0.6 and 6 degrees. And of course there's a difference between the values of the MPE for different angular substances, and that can be seen in the next slide for one wavelength type, 400 to 600 nanometers. For 1, 10 and 100 milliradians. And you can see that if alpha is smaller, then the laser spot will be brighter, and then the MPE, permissible MPE, will be smaller as well. And you can see it here. The calculation. The safety condition is that the intensity must be smaller than the maximum permissible exposure. E is the intensity, I is the proportional to the laser power, of course, and I is 1 over the target area in square meters, and I will be dependent on the type of laser beam, and that's expressed in the profile correlation factor. And this means that we can give an expression that I is P over S times that profile correlation factor, and this is the formula. What is the profile correlation factor? Well, the local modes in local intensity in modes of the laser is larger than average over the envelope of the laser. Here we have different transverse modes and rectangular transverse modes of the laser, and this means that you have to correct for that intensity, and therefore the profile correlation factor dependent on the mode structure is taken larger than 1, except of course for here. The safety condition. I is the intensity at the target, P is the power, PC is the profile correlation factor, and S is the target area, and that must be smaller than the maximum permissible exposure. And this means that the S, the target area, must be larger than the power times the correlation factor divided by the maximum permissible exposure. This is our situation. We have a laser. This is the distance to the focus, A. The distance to the target is called R. The diameter of the target is D, and the angle is theta. The total angle is theta. The width of the focus is W. The effective target area is S is pi over 4 times D prime squared, and D prime is D plus W, because the focus with W has to be taken into account. D prime is called the effective diameter, and this means that the target area is given by pi over 4 times D plus W squared, or 4S over pi is D plus W squared. So D can be written as the square root of 4S over pi minus W. And when we insert this expression for S, we end up with the expression here, 4P times PC over pi times the maximum permissible exposure. And this expression we will use for the derivation of the NOHD. Effective target area again, and the safety condition for the target diameter was given in the previous slide by this expression. And now the NOHD is defined as the R plus A for which this condition holds, and that's D over 2 times tangent half theta, D over 2 times tangent half theta plus A, and that is written as 1 over 2 times tangent half theta times this expression here for the D plus A, the distance to the focus. Here is this expression again, and you can see that the D depends on the NOHD depends on the diameter of the target, or the theta angle, the square root of the power, the square root of the profile correlation factor 1 over the square root of the maximum permissible exposure, the width of the focus, and the distance from laser to focus. But the NMHD is also dependent on the angular subtens, and that's the angle in which you can view the source from the target position. And that's depicted here. This is the width, and this is the angle alpha, the full angle alpha. And this means that the tangents of half alpha is half width over r, and that is width over 2 times the NOHD minus a. And you can see that the smaller waist will lead to a sharper spot and NPE will be lower. And for certain situations, especially for visible light situations, the maximum permissible exposure depends indeed on the alpha, as we have seen before in the plots of the NPE, and thus it depends on the NOHD itself. And so we have two relations between the NOHD and NPE. First, the expression of the angular subtens, in which the tangents of half alpha is coupled to the NOHD. So the NOHD is a function of alpha. And the second one is expression with the MPE, as we have seen before. And this means that the NOHD is also a function of the MPE, the maximum permissible exposure. And that is a function of alpha from the safety condition. And here we had that NOHD expression. So we have two expressions for the NOHD and the MPE. And this means that we need an iterative approach. We have two relations. The first is from the NOHD. The amp is a function of the MPE, maximum permissible exposure, and that is a function of alpha. And here we have from the angular subtens that the NOHD is also a function of alpha here. And so we have that iterative approach. We start with an alpha value, and then we calculate the NOHD from equation 1 and from equation 2, and compare both to a certain tolerance, for instance 1 over 10 to the 6 or so. If the difference is smaller than the tolerance, then we are ready, but if not, then we have to change the alpha a little bit and calculate again, and go on until we reach that situation. And that is what is done in the computer programs. The transmission of safety goggles. In case the NOHD is larger than the safety distance from the focus, safety goggles are necessary. The transmission of safety goggles and the optical density are given by the transmission is B squared over NOHD min A squared, and that's the optical density is minus the logarithm, the 10 logarithm of the transmission. The target area is proportional to R squared. And for this transmission, for this safety distance B, is used 0.25 meters for a 10-second exposure, as we have seen before. In order to treat the laser treatment in our computer program, we consist a laser treatment consisting of a lot of trains, separate trains of pulses, and this is the total treatment. Here we have the trains with pausers in between, and each train contains a lot of pulses. And of course, for continuous lasers, you can calculate one long train of one long pulse. This is an example of the calculations. We have a standard laser input here with the wavelength is 532, divergence angle, profile correlation factor, a spot diameter here, the distance of the laser to the focus, and then the laser pulse. There's a pulse power of a megawatt, a pulse energy here, and pulse duration is 5 nanoseconds, and the repetition frequency is 1000 Hz. Of course, these values are connected. There is a train of pulses, in which the number of pulses per train is 10,000, and this is the power of the train, the energy, and the duration. And then we have a total treatment with one train, of course the same power as the train, the same energy as the train, and the duration is the same because there is only one train. And the safe distance from the focus for glasses is 0.25 meters. And here we have an example of the calculations. The program gives the possibilities for damaging and the results for the eye in the pulse, the train, and the total, for the skin, pulse, train, and total. This is the formula as used in the directive of the European Union formulas. This is the maximum permissible exposure that's valid for this time region. This is the alpha that is resulting from the iterative approach, the NOHD in meters, the transmission of glasses, and the optical density of the glasses, and a correction factor that is needed for thermal damage. And this is the end of the first part of the of this presentation. Now we go further with the second part, and that is an introduction to the computer program. And this is the second part of the presentation, the laser program part. We have the laser part of the large gigahertz program, which is mostly in Dutch, but not the laser part. Here again, we start with a description of the time scheme of the laser treatment with trains and intermezzos, and each train may contain different pulses. Here we have an explanation of how the program works and what has to be inserted. Here we have the data we need for the wavelength, the divergence angle, the profile correlation factor, the spot diameter, the distance to the laser, information about the pulses, power, energy, duration, the train of pulses, and the total treatment. And of course, part of these values will be coupled because of the power expression, power, the energy, the duration, and the frequency will be coupled, and so on. Here we have the switches. We can plot the MPE or calculate MPE directly, as can be seen here. For instance, for a pulse length of 1 microsecond, a wavelength of 600 nanometers, and an alpha is 1.5 milliradian. And then we can calculate the MPE. And these expressions here are constants that are used in the European directive. And here we have the MPE, the maximum permissible exposure for different situations. We also can perform the graphics as we have seen before. For instance, here for 400 nanometers, as we have seen for the eye, and then for 400 nanometers, the ID, the figure is as is depicted here for different values of the alpha angle, the subtense angle. For 800, 800 nanometers. For the eye, it looks like this. But now we go to calculation of the laser. We use a standard laser with the values as seen here. In pulse type, we use as the starting point for the calculations the power and calculate from the power the energy. We have to change the values in the table, and the values with asterisk will be calculated, and cannot be changed in the program. The test of the input data is needed to be consistent, because of course the values has to be connected. We can show the iterations in the calculation and calculate the NOHD. First, the program gives what kind of damage is to be expected for the eye and for the skin, and then is there a thermal correction needed, and the thermal correction is only for thermal damage. But that is all explained in the program description. Here you see all the iterations, and again for the wavelength the damage is given by here. The number of pulses and trains is smaller than a certain minimum time as is given in the EU directive, and no thermal correction is needed. And here the calculations are ready. Here is the formula. This is a constant used in the EU directive, as is the T2, but here we have the MPE, maximum permissible exposure, the alpha angle, the angular subtense, the NOHD, the nominal ocular hazard distance, transmission of the glasses, and optical density of the glasses. The output can be given in text form, as we have seen before, or in comma-separated value form. And here is the output in text form, output calculations. AAA, for instance, want to view the file, and this is the output file. Thank you very much for your attention.